So, shall we start the program?
I'm ready.
Okay. Good evening, all. I welcome you all to this session. We are going to start session 5, that is the first online session of Quaesitio 2024 International Conference on Sustainable Development for a Better Future. Here we have Dr. Dattani from High Performance Quantum Computing Lab, Canada. I invite Dr. Thomas Matthew, Assistant Professor, Department of Physics and Stephens College, Udavu, for introducing our resource person and for the welcome address.
Sorry, I lost the connection. Sorry for the trouble. Dear participants, I am delighted to introduce my friend Dr. Dattani in this session. Dattani was born in Toronto, Canada, and did his undergraduate degrees in physics, biology, and mathematics. And then he completed his PhD at Oxford University in computational chemistry. He has also worked in computer science and engineering departments in Canada and Singapore, and in science departments in Japan, US, and Germany. He is known for inventing the MLR model for potential energy curves, which is now widely used in more than 100 publications and for breaking records on quantum computers. He has also created the Matter Modeling Stack Exchange, which now has more than 7,000 members and serves as a high-quality site for questions and answers about the modeling of matter and for related software. Without further ado, I extend a warm invitation to Dr. Dattani to deliver his talk.
Thank you for the introduction. Is everyone able to hear me?
Yes,
is my voice okay?
Yes, fine.
Okay, excellent. So I've had this warm-up slide up for a while. Quantum computing is a very technical topic. I think for the most part, the physicists and mathematicians in the room will gain a lot from this talk. Being able to do these matrix vector multiplications, it's a prerequisite for quantum computing. So I have put this warm-up slide as my first slide, just so that you know the answers. This vector, it's 0, 1. This one, it's 1, 0. And I will talk about this one a little bit later. So this is my introduction to quantum computing. I will start by explaining this experiment. This is an experiment that was published in 1891. This is a paper by Zander, and in German, it says a new interference refractor. And that is this device over here. If this paper was published in 2024, this diagram might look more like this. So this is the device that was introduced in this 1891 paper. It's called an interference refractor. And this has now become known as the Mach-Zehnder experiment. What we do is we put photons. Photons are going to we're going to shine photons on this half-silvered mirror. This is a piece of glass where we sprinkle silver on the glass. So it is sprinkled such that 50% of the glass is covered by silver. When the photons go through this half-silvered mirror, 50% of them will just go through the glass. 50% of them will hit a piece of silver, and they will be reflected. So this will be a 50% probability of the photons going through if they go through the glass, and a 50% probability of the photons being reflected by the silver. Now here we have a full silvered mirror, and here we have a full silvered mirror. This is complete pure silver. So any photon that hits this pure silver, it will be reflected, okay? And so we're gonna have, these photons are gonna be reflected, these ones will be reflected, and then we go through another 50-50 beam splitter, a half silvered mirror here. So my question now for the audience, if we were to detect the photons over here and over here, what percentage of the original photons do we expect to find over here at the top and over here at the side? If someone can answer in the chat, then I'll know that you're following along. So the question is, what percentage of these original photons do we expect to find here at the top and here at the side? So 50% of them will go here, 50% of them will go here, and then it's going to go through another beam splitter. So this 50%, that's now going to go through this device again. I see a lot of answers. I think the host of the meeting has said 50% and 50%. So this was one of the answers that was given in the chat. And I will explain how that answer was obtained. We have 50% of the photons here. When we go through the 50-50 beam splitter, this 50% is going to become 25% and 25%. This 50% of the original photons is also going through a beam splitter. We're going to have 25% here and 25% here. So this adds up to 50, and this adds up to 50. I hope everyone understands that. At least some of the people in the chat seem to understand it. So in classical mechanics, if photons are treated as particles, a particle that is either here or there, we expect to find 50% of the photons up here and 50% of the photons there. Now, I might surprise all of you by saying that when this experiment was done, 100% of the photons were detected here. 0% of the photons were detected up here. This might be a surprise for everyone because it doesn't make sense in terms of the laws of probability. It doesn't make sense in terms of our understanding of photons as particles. It doesn't make sense in any way that we would understand in classical mechanics. But the answer, there is a good answer to this problem. There is actually a reason why we detect 100% here and 0% there. And in quantum mechanics, photons are not always treated as particles, a particle that is either here or there with 50% probability. But a photon can act as a wave, okay? A wave. Waves can have constructive interference and destructive interference, and waves are delocalized. A wave isn't just here or over there. A wave looks delocalized, okay? So it's like the photon is in both paths at the same time. I will explain this in more detail as I start to explain a little bit about quantum computing, okay? I'll first talk about qubits. We represent qubits using this notation. So this is a qubit and this is a qubit. This qubit represents this vector 1, 0. This qubit is 0, 1. We have zeros and ones just like we do in classical computing, but these zeros and ones are represented by vectors. And quantum gates, these are like logic gates, but for quantum computers, they are represented by matrices. So this gate over here, the X gate, if we apply this X gate to this vector, to this qubit, we are multiplying this matrix by this vector. So if we imagine this matrix is here and this vector is here, this was the warm-up exercise that we did at the very beginning. So what answer would I have here? Maybe someone can type it in the chat if you remember from the warm-up exercise at the beginning. Good. 0, 1, that's this qubit here. So the 0 becomes a 1. The 1 also becomes a 0. Okay? This, in classical computing, this would be called the NOT gate. It turns a 0 into a 1 and a 1 into a 0. It's the same thing in quantum computing. We have a 0 becomes a 1 and a 1 becomes a 0 because of this matrix multiplication. That's the answers that I gave over here. In classical computers, we have bits. These are zeros and ones. They represent distinct classical states. For CPU processing, zeros and ones represent low voltage and high voltage. In barcodes, the zeros and ones, they are thin lines and thick lines, okay? In a disk, like a CD, DVD, or Blu-ray, we have microscopic pits, zeros and ones. This disk is going to be spinning. There's a laser that detects whether we have a pit or no pit. If there's no pit, that's an absence of a pit. This is a 0. This is a 1, where there's a presence of a pit. Sorry, this is a pit. That's a 1. This is no pit. So that's a 0. And the difference between the CD, DVD, and Blu-ray that we can see here is the density of zeros and ones. Okay? So in the CDs, you might have a few megabytes. In the DVDs, you might have a few gigabytes. In the Blu-ray, you might have more gigabytes of data. Also in hard drives, we have zeros and ones. These are, we can consider these to be magnets that are either north polarized or south polarized. We can also have computers or storage devices using DNA molecules. These are organic computers. So we have AT and CG. This is AT, that's a 1. This is CG, that's a 0. And the human genome has 3 billion base pairs, so 3 billion zeros and ones. In just a DNA molecule that is stored in a cell, which might be 0.2 micrometers in diameter, we have 3 billion bits of data. That is almost a gigabyte of data in just 0.2 microns of diameter, within even smaller than that. And this is completely organic and biodegradable. So this magazine front cover was about DNA computers. This was in March 2005, okay? But the idea goes back to 1990s. A person named Leonard Edelman, a computer scientist who came up with the idea of computing with DNA. But all of this is still classical computing. We have zeros and ones, and these are distinct states. You're either AT or CG. That's still a 0 or a 1. In a quantum computer, we have qubits. We still have zeros and ones, but they are now 2 quantum mechanically allowed states, rather than just 2 classically allowed states. So if we have an atom, the electron could be in the ground state or in an excited state. This will be our 0 and our 1. For spin, we can have spin up and spin down. We could also have photons, horizontal polarization and vertical polarization. And there's more possibilities, okay? Superconducting qubits, transmons, various different possibilities are available. Now, the Schrödinger equation tells us if we have a quantum mechanical state given by this object over here, 10 seconds later, if we want to know what the quantum mechanical state is, we plug in t equals 10 seconds. We plug t equals 10 seconds into this equation. And this here, it's a matrix. If we know the Hamiltonian h, and we know the amount of time t equals 10 seconds, we will get the quantum mechanical state 10 seconds later. So here we have the matrix. We want to implement the NOT gate. 0, 1, 1, 0 is the matrix. We just need to make the Hamiltonian and the amount of time that we're applying the gate to be chosen such that we have exactly this matrix converting our initial qubit into the new qubit. So by doing that, by choosing the right Hamiltonian and the right time, the right amount of time, we will be able to turn the 0 qubit into a 1 and the 1 qubit into a 0. However, in classical computing, we are limited in the number of gates that we can have. In quantum computing, we have more possible gates. In fact, we have an unlimited number of gates. These are just some of the gates we can have in quantum computing. We can have negative numbers, we can have imaginary numbers, we can have fractions, and we can have an unlimited number of gates as long as this matrix has certain properties. But we can have an unlimited number of gates. So now let's demystify that Mach-Zehnder experiment. Why did we find 100% of the photons here and 0% of them here, even though everyone said in the chat that we should have 50% there and 50% there? Why did this happen? I'll explain this in terms of qubits. So if we have a qubit 1 representing this path and a qubit 0 representing this path, we start with this qubit 1. This qubit goes through this beam splitter. This beam splitter is represented by this matrix. When we operate on the qubit with this operator, this is the result we will get when we do the matrix multiplication. So we start with this vector, which is 1. We do the matrix vector multiplication, and we get this vector here. In the warm-up exercise, I told you, take this vector and split it up into a linear combination of its basis states. So here we have a fraction, I over root 2, and here 1 over root 2. So we are partially in this 1 path and partially in this 0 path. Instead of trying to say that 50% of the photons are here and 50% of the photons are here, we are going to say that 100% of the photons are in this state. This is how the qubit is represented now. 100% of the photons are now in this state. What does this mean? When we have a coefficient in front of the 0, it means the probability, if I put a detector here, the probability of finding a photon here in the 0 path is going to be the absolute modulus of this coefficient squared. That equals 1/2. Likewise, the absolute modulus of this coefficient squared is equal to 1/2. So this actually makes sense in terms of what we understood before. This half-silvered mirror, we thought that it's taking 50% of the photons and making them go through, and 50% of the photons and reflecting them upwards. But really, we only thought that it was doing that because classically, if we put a detector here, we get 50% of the photons appearing here. And if we put a detector over here, we would get 50% of the photons appearing there. And that is still the case with this quantum mechanical model. It's still the case that 50% of the photons will be detected here, and 50% of the photons will be detected there. It is just that 100% of the photons are in both states at the same time until you do the detection. So if you've heard of Schrodinger's cat, the cat is alive and dead at the same time until you open the box. Here, the photon is in both this state and this state. It is in both this path and this path at the same time. 100% of the photons are in both states at the same time, such that when you do a detection, when you open the box, you find that the cat is 50% alive, 50% dead. If we put another half-silvered mirror here, then we start with this qubit 1. We have one half-silvered mirror here and another half-silvered mirror here. We do 2 matrix multiplications and we end up with this vector here. This vector, I0, that means we have nothing in the 1 state and I in the 0 state. So that's our final state here. What is the probability of finding the quantum mechanical state or the photon in this 0 path? Remember, this was the 1 path, this was the 0 path. What is the probability of finding the photon in this path? It is the modulus of I squared. That means 1. So we have a 100% probability of finding the photon in this position here. So this is the explanation for why we got that experimental result. This quantum mechanical theory, it works in explaining this experiment. It also works in explaining the classical experiments you might do earlier, where you do a detector here. You'll still get 50% here, 50% here. But the difference is that this theory, it actually successfully predicts the experiment where we have two beam splitter. And it's because of the nature of these matrices. What's happening is we're taking quantum mechanical states represented by this model of vectors, and we're doing things to those vectors. And this is how quantum computing works. Instead of having just ones and zeros, we can have 1 and 0 at the same time. So the question you might now have is, how can you use this to make a more powerful computer? And this is something that was originally proposed by David Deutsch. David Deutsch, who was a professor at Oxford University, came up with this idea where we have a variable which is either 0 or 1. And we have a function of that variable, f of x. How many times do we need to evaluate f of x if we want to know whether or not f of 0 plus f of 1 equals 1? How many times? Someone in the chat might be able to give an answer. Now, this question is not a trick. How many times do we need to know? How many times do we have to evaluate f of x if we want to know whether or not f of 0 plus f of 1 equals 1? 2, that's the correct answer. So if we want to know whether or not f of 0 equals f of 0 plus f of 1 equals 1, we have to know f of 0 and f of 1. So if f of 0 and f of 1 are both 0, the sum will be 0. If f of 0 and f of 1 are both 1, the sum will be 2. If f of 0 and f of 1 are different, then we will have a sum of 1, which is what we want. Okay, so if f of 0 and f of 1 are the same, we will get a 0 or a 2. If they are different, we will get a 1. And then the question is, how many times do we have to evaluate f of x if we want to know whether or not f of 0 and f of 1 are different? And the answer is that you have to evaluate f of x twice. Now, in a quantum computer, these simple gates are enough to determine f of 0 plus f of 1 with one evaluation of the function f of x. Instead of checking f of x for 0 and then for 1 and comparing them, we are just going to check f of x for this superposition of 0 and 1. Here we are checking 0 and 1 at the same time, okay? We have a qubit that is in both the 0 and 1 states at the same time, and we apply these quantum mechanical gates. There's a matrix representation for these gates. And what that does is we have the qubit starting here. We apply this transformation, this gate over here. We have a matrix that applies to that vector. Here we have another gate. It applies another transformation to that vector. And by only evaluating this quantum mechanical gate representing the function f of x, if we only apply it once, okay, we're applying f of x once to this qubit, we will end up with this state over here. Now you can go through the mathematics. If f of 0 and f of 1 are both 0, we will have 1 plus 1. These exponents are 0, okay? 1 plus 1, that's 2. 2 over 2, that's a 1. Here we will have 1 minus 1. That's equal to 0. So we'll have 0, 1. That's our vector here. We have 0, okay? Sorry, we have 1. This is the 1, and that's a 0. So we'll have the 1 vector here. 1, 0, that's the 0 vector. Likewise, if f of 0 and f of 1 are both 1s, we will have the same thing. This negative sign, that just means that when you do a measurement, you have 100% probability of finding the state in the 0 state. But if f of 0 and f of 1 are different, we will find the qubit in the 1 state. So when we do the measurement, if f of 0 plus f of 1 equals 1, there's a 100% probability that the wave function in the end will be in this state, 1. If f of 0 and f of 1 are different, there's a 100% probability that we'll have the qubit in the 0 state. So if we measure a 1, basically if the photon is in this path, that means that f of 0 plus f of 1 equals 1. We only had to evaluate this function 1 time. So basically, we have 2 complicated gates applied to 1 qubit, and we have the answer to the problem. On a classical computer, we might have some simple gates applied 2 times, and we will get the answer to the problem. This was done in a real experiment. The quantum mechanical gates were done in a real experiment in 1998. This was done by Michele Mosca, who was my quantum mechanics instructor, my quantum computing instructor when I was a student. Now we can scale this to a much larger scale, okay? So David Deutsch and Richard Josa in 1992 came up with a generalization of this problem, where we have xi as a variable, it's either 0 or 1. We have many variables here, x1, x2, x3, up to xn. How many times do we need to evaluate this multivariable function in order to know if it's constant? What I mean by constant is, for example, if there's 3 variables, this gives me 0, this gives me 0, this gives me 0. Any input, these input variables, if they're 0s or 1s, it doesn't matter. Whatever my variables are, I will always get the same output. How many times do I have to evaluate this multivariable function in order to know if it's a constant function? This is again something you can answer in the chat. Two to the n, that's very good. Okay, sometimes people say n, that's not the right answer. The number of possible, you need to know every single possible output for this function. So if I give you 1, 1, 1, is it a 0 or a 1? I need to know that. If I give you 0, 1, 0, I need to know, is it a 0 or a 1? You need to know the result of applying that function for every possible input in order to know if this function is a constant. So that means we have to check, this could be a 0 or a 1. This has 2 possibilities. This has 2 possibilities. This has 2 possibilities. You have to check 2 to the power n different possibilities. You have to evaluate the function all of these times in order to know whether or not the function is a constant. Now you're going to see the power of the quantum computer. So the quantum computer only needs to evaluate this function 1 time in order to know whether or not the function is constant. Only 1 time, okay? And the reason for that, this was the circuit for the Deutsch algorithm, the solution to the Deutsch problem. For the Deutsch-Josa problem, we're going to do something similar. We're going to have n qubits, okay? So there's 1, 2, 3, up to n qubits. Each of these qubits is going to be in a superposition of 0 and 1. 50% 0, 50% 1. It's a little bit of both. And it's going to go through, and we're going to evaluate the function f of x 1 time. This gate, it's applying f of x to all of these qubits at the same time. On a classical computer, you can have something like the AND gate, where if you have 0 and 0, this gives me a 0. Or if I have 1 and 1, this gives me a 1. So we have 2 inputs and 1 output. Here we have n inputs and 1 out. We have n inputs and I don't know how many outputs. Here we have n outputs as well. So it's a multi-qubit gate. but that multi-qubit gate is only evaluating the function f of x once. That's the way the gate is designed, but it is evaluating this gate on all of these qubits at the same time. This was done in a real experiment in 2002. One evaluation of the function f of x was enough to determine whether or not the function was constant. So that's the Deutsch-Jozsa problem. And the most famous quantum computing algorithm, the one that everyone's heard of, it's Shor's algorithm for factoring integers. It's actually not much more complicated than the Deutsch-Jozsa problem, okay? The circuit for solving the Deutsch-Jozsa problem on a quantum computer, it's not much different from the circuit for solving the factorization problem with Shor's algorithm. Instead of the Hadamard gates here, we have an inverse quantum Fourier transform. And instead of this gate, which I was able to write down very easily, we have a unitary gate here, and we have some auxiliary qubits here. But it's not much more complicated. So in 30 minutes, I taught you how to solve the Deutsch-Jozsa problem on a quantum computer. In another hour, I could teach you how to do Shor's algorithm. That's the most famous quantum mechanical algorithm. If you were to take a full course on circuit-based quantum computing, we would teach you how to do machine learning on a quantum computer. Instead of 2 to the 9 evaluations, you might have instead of 2 to the n evaluations, you might just have 1 evaluation. We could teach you how to do quantum computing for financial applications, quantum money, quantum cryptocurrencies, quantum communication, quantum internet, quantum security. You can imagine if you want to find the password and you want to, you can only try one time to get the password. Instead of evaluating 2 to the n times for an n character password, we can do it maybe by checking only once, okay? Quantum decoherence, that's a physical phenomenon. How to actually implement quantum gates, how we physically actually make quantum computers with superconducting qubits, photonic qubits, spin-based qubits, nuclear magnetic resonance, NV centers, nitrogen vacancy centers, ion traps, Rydberg atoms, ultra-cold molecules. There's various ways to make quantum computers. And I offer a course on quantum computing, online, in person, wherever you live. You can email me at nikkei@hpqc.org or info@hpqc.org. If you're interested in learning more about quantum computing, I've only given you the introduction. I will now run through something very quickly, adiabatic quantum computing. It's a much simpler way to do quantum computing. So you don't need those gates the way I showed you. There's no matrix multiplications anymore. And in the last 10 minutes, I'll just try to get through one example of adiabatic quantum computing for factoring the number 143. So this is what Shor's algorithm would do if I taught you what the inverse quantum Fourier transform was and all that. But now I don't need to do that. I can just show you this in a way that I think high school students would understand. So we have P times Q equals 143. We want to factor the number 143. We have P times Q equals 143. We want to know P and Q. We don't know P and Q. We know that the last bit is a 1 because it's an odd number. If it's an even number, if the last bit is a 0, we have an even number. If we want to factor an even number, we just divide by 2. We just keep dividing by 2 until we have an odd number. So the interesting case is where P and Q are prime. They're ending in 1s. And the first bit has to be a 1 because if it's not a 1, then it's not the first bit. So P1, P2, Q1, Q2, these are all variables. And we're going to multiply P times Q to get 143. Now, when we do this, we get a set of equations. When we do this long multiplication, the way we did when we were 10 years old, we will get a set of equations. Now, someone tell me if A and B and C are all 0s or 1s, what is the value of C? If A, B, and C are all 0s or 1s, you can answer in the chat. 0, that's good. Yes, C equals 0. Because if C equals 1, then we would have 3. There's no way that 1 plus 1 can equal 3, or 0 plus 1 can equal 3. There's no way that the left side could be a 3. So the right side would be a 3 if C equals 1. So C has to be 0. Because of that, we know in this first equation, Z12 has to be 0. Okay, I'll make that clear for you again. Z12 has to be 0. Because if it was a 1, we couldn't satisfy this equation, possibly. So we know that Z12 equals 0. So basically, we compile our code before we run it. We want to factor 143. Z12 equals 0. We know also some of these are zeros. We end up with a simpler set of equations here. Okay? So we end up with this simple set of equations. One of them is P1 plus Q1 equals 1. We've eliminated a lot of the variables by using the type of logic that some of the people in the chat were able to figure out. So P1 plus Q1 minus 1 squared. I'm going to start with this equation, and I'm going to square it. Someone tell me what the minimum of this function is. The minimum of this function. P1 and Q1 are either 0 or 1. So what is the lowest that this function can be? And everyone's doing very well in the chat. Everyone's getting the right answer so far. Zero, very good. The minimum is 0. We are squaring this number, so it cannot be negative. And the lowest it can be is 0. If P1 is 0 and Q1 is 1, then we'll have a 0. If we're squaring a number, it cannot be negative. So the lowest it can be is 0. So the solution to P1 plus Q1 equals 1, it's the same as the minimum of this function. If we minimize this function, we will find the P1 and Q1 such that P1 plus Q1 equals 1. Okay, that is what we're doing there. And then let's see if someone knows the minimum of this function here. What's the minimum of this? It's just as easy of a question. What's the minimum of this question here? The minimum of this function here. To speed things up a little bit, I'll ask, can this function be negative? Is it possible for that function to be negative? No, it's not possible for this to be negative. So what's the minimum? 0. Very good. Okay. So if I minimize this function, that means that I'm satisfying this equation, and this equation. And remember, by satisfying these 3 equations, we are factoring the number. Factoring the number means we're finding P and Q such that P times Q is 143. That just means solving this set of equations. This set of equations is equivalent to this small set of equations. So I need to satisfy 3 equations in order for P times Q to equal 143. And I'm satisfying all 3 of these equations by minimizing this function. If I find the P1, Q1, P2, Q2 that minimize this function, I'm finding the P1, Q1, P2, Q2 that satisfy this equation, and this equation. Because all 3 of these have to be 0 in order for this function to be minimized. So factoring the number is equivalent to finding the minimum, finding the P1, P2, Q1, Q2, such that this function is minimized. Now, physically, we can treat these P1s, P1, P2, Q1, Q2. We can treat them as qubits, either 0 or 1. Each of them is either a 0 or 1. And we can evaluate the function for each of these qubits for each of these variables. And we find that the minimum is 0 at 2 locations. One of them is p equals 11, q equals 13. One of them is p equals 13, q equals 11. Those are the factors of 143. So we have factored the number 143 without doing much work. We have just minimized the function, and by doing that, we found the p and the q such that p times q equals 143. We have 4 variables. If we wanted to do this on a classical computer, we would be searching for the minimum of this function. We would be checking all of these different possibilities for P1, P2, Q1, Q2. We would be checking 16 different possibilities. On the quantum computer, we're just finding the minimum of this function, okay? If I had 5,000 variables, if I wanted to factor RSA 230, a huge number, then we would be searching through 2 to the 5,000 different possibilities and finding which one is the lowest, where is the minimum 0? It's here, it's here. If we're searching through 2 to the 5,000 possibilities, it's not sustainable. However, if we make a quantum computer, I'm going to take you back to high school chemistry. Each atom has this electronic configuration represented this way. We have electrons that are either spin up or spin down, okay? Spin up or spin down. These are 1s and 0s, essentially. So 1 and 0, we can call it 1 and 0. Now we have these variables, P1, P2, Q1, Q2. I'm just going to call them all bits, B1, B2, B3, B4, okay? And I'm going to look at this Hamiltonian. This is the Hamiltonian that describes how these qubits are interacting. B1 and B3 are coupled with a coefficient of 2. B1 and B4 are coupled with a coefficient of 1. So B1 and B3, I'm going to take these 2 electrons. These are 2 spin-up electrons. I'm going to couple them with a strength that is twice as big as the coupling between B1 and B4. So this is B1 and B4. There's some coupling strength, but I'm going to couple B1 and B3 with twice that coupling strength. So I'm just going to take 4 electrons or 4 hydrogen atoms or 4 protons, anything with a spin up, spin down, as long as there's a spin up, spin down. I'm going to take those quantum mechanical objects and I'm going to couple them with strengths proportional to the coefficients in this function that I want to minimize. And here's what I get in the end when all of the qubits are coupled to each other. I have B1, B2, B3, B4. This is 1, 0, 1, 1. The ground state, the configuration of electron spins, whether they're up and down, when they are coupled with these strengths, the configuration with the lowest energy, the ground state, if we cool it down to absolute 0, it's going to be 1, 0, 1, 1. That's the answer to the question. We want to factor 143. We're going to get P equals 13, Q equals 11. I showed you before, P equals 13, Q equals 11 corresponds to P1 equals 1, P2 equals 0, Q1 equals 1, Q2 equals 0. So here we searched through 2 to the 4 possibilities, but we didn't actually have to do a search on a classical computer. Instead, we just took 4 electrons, we coupled them together with certain strengths, and we found the ground state. And the ground state told us the answer to the problem. If we had 5,000 variables in our factorization problem, if we wanted to factor a big number, on a classical computer, we're searching through 2 to the 5,000 possibilities. On the adiabatic quantum computer, we just need 5,000 electrons or 5,000 protons. 5,000 electrons is not a lot. There's 100 trillion cells in the human body. 100 trillion cells in the human body. Each of them has millions of electrons, right? So 5,000 electrons is not very much. That's sustainable. It's sustainable to come up with 5,000 electrons. So a long time ago, I asked my undergraduate student, Nathan Bryant, my undergraduate student, I said, write me a program such that I give you a number and you give me the Hamiltonian or the function whose minimum factorizes that problem. And 2 days later, we had this Python script that gives me these answers. So I start off with that table that I showed you before. We have the set of equations. It solves some of these equations just like you did when I had a plus b equals 1 plus 2c. We get this simpler set of equations, and we managed to factor 56153 with only 4 qubits. Nathan Bryans, he was an undergraduate student at the time. We published a paper. He is now a director of artificial intelligence at ATB Financial, one of Alberta's biggest financial institutions. This was picked up by journalists. They considered this to be the new largest number factored on a quantum device, 56153. Some people called this the mathematical trick that helped smash the record for the largest quantum factorization. I like this article, NSA Plans for a Post-Quantum World. They referenced my work there. But the biggest honor was when the RSA crypto system, this is a security system. It is named after Ronald Rivest, Adi Shamir, and Leonard Edelman. Now, I mentioned Leonard Edelman before. He's the computer scientist who not only works in computer security, but he invented DNA computing, which is what I talked about a long time ago. In the 1990s, he came up with an idea about how to actually do computing with DNA, where AT equals 0, CG equals 1. But Ronald Rivest was one of the authors of that RSA crypto system. And in 2015, he gave this talk at Berkeley where he mentioned my work. So that was the biggest honor for me. And later on, we factored the number 291311. So that's a bigger number, more digits. My undergraduate student, Richard Tanburn, he was a co-author here. He is now a permanent researcher at Google's DeepMind. And in 2021, they published this paper about advancing mathematics with artificial intelligence with my friend Alex Davies. And at the end of 2021 on Math Overflow, people were asked, what is the biggest breakthrough in mathematics in 2021? The highest voted answer by Carlo Bienecker was this paper by my undergraduate student, Richard Tanburn. So this is a field, it's a new field, it's exciting. A lot of junior researchers at the undergraduate level can make big contributions and go on to have great careers. With Shor's algorithm, we have been able to factor some small numbers. With the adiabatic algorithm, we have been factoring larger and larger numbers now. And so adiabatic quantum computing, all it is we encode the solution to our problem in the ground state of a Hamiltonian, and then we find that ground state of the Hamiltonian. That's all we do. We can do this for quantum chemistry if we want to model pharmaceutical drugs, if we want to study chemistry, if we want to study materials. Quantum chemistry involves finding the ground state of this Hamiltonian. We can do a Jordan-Wigner transformation, and we end up with a Hamiltonian like this, okay? Where these are operators acting on each qubit. We can basically find the ground state of this Hamiltonian for, in this case, 4 qubits. And then we have the ground state energy of the H2 molecule based on the basis set that we're using. So one of the issues, what I've been talking about all day today is how to compile your problem, whether it's factoring numbers or solving quantum chemistry problems. I've been talking about how to compile these problems so that they run on quantum hardware. Turn it into a minimization problem. Remove unnecessary qubits. There's more to the story. Quadratization. If you have 3 qubits interacting at the same time and the hardware only can couple 2 qubits at the same time. Graph embedding to make sure that the connectivity of the variables in our function matches the actual quantum hardware. And I can compile your code to run on quantum hardware if you don't want to do it. We have 100 QPU hours per month on the D-Wave machines, 400 QPU hours on the IBM Q20X, and $10,000 of QPU time available on the IonQ quantum hardware. Alternatively, if you still prefer classical computing, I thought that I would just let you know. You can collaborate with us. We have 2 petabytes of disk space, 800 CPU years per year. So every year, you can have 800 CPUs running for the full year. Okay, so that's the amount of computing power that we have if you want to work with us. With that, I thank you for your attention. I'm also happy to answer any questions that you might have.
Thank you, sir. We move on to discussion. Those who have any doubt, please feel free to ask.
I'm prepared for your questions. If you have any questions, I have preparation for this, okay? I know this is a conference on sustainability, so I thought that I would show you that a quantum computer in 2016, an adiabatic quantum computer, found the solution to a problem with 900 bits, an optimization problem with 900 variables. In here we have 10 to the 4 microseconds. The best classical computer at the time, using quantum Monte Carlo, 10 to the 11 was the amount of microseconds that it took. So 7 orders of magnitude, 10 million times longer it took the classical computer to do the calculation compared to the quantum computer. And this was done by Google. Hartmut Neven, the director of the quantum lab at Google, he said at a conference in 2016 that $1 million went into this classical computation. So if you're 10 million times faster than the classical computer, the next thing you might wonder is about the energy. How much energy is being used in the quantum computer versus the classical computer? 12 kilowatts of power. This is from, sorry, this is nasa.gov. They say that it's 12 kilowatts of power for this quantum computer. That's the computer that was used in that paper. If you look at the green 500, these are the 500 most environmentally friendly supercomputers in the world. The most environmentally friendly computers that are in the top 500 list of biggest supercomputers in the world. The best one in the green 500 uses 50 kilowatts of power. The quantum computer uses 12 kilowatts of power. In this case, where you're 10 million times faster than the classical computer, that means that if you have 10 million cores or 10 million CPUs in your classical computer, you can parallelize this calculation and maybe compete with the quantum computer. 10 million cores. However, the biggest supercomputer in this green 500 list, in the top 5 here, you have a computer with, 19 million cores. So let's say this is 20 million CPUs in one computer. This can actually run the calculation faster than the quantum computer, because the quantum computer is only 10 million times faster. So this supercomputer can actually do the calculation 20 million times faster than doing it with one CPU. So it's twice as fast as the quantum computer, but it's using 1,350 kilowatts of power. The quantum computer is using 12 kilowatts of power. So it's 100 times more energy efficient. This is the Oak Ridge National Lab Summit supercomputer, where you have, for example, that I showed you something with 20 million CPUs in one supercomputer. This is using so much energy that it could light up a small city. The quantum computer is just this, okay? That's just the quantum computer, one box. That's the classical supercomputer that has 20 million or more cores or CPUs. I would be happy to answer any questions. I see 2 questions here. How can a master's student start working on a quantum computer? You can start with me if you want. I had undergraduate students that were publishing landmark papers, breaking records for quantum factorization 10 years ago. Now all that stuff is old. That's not interesting anymore. But at the time, these were big discoveries, and some of those undergraduate students went on to get jobs at Google's DeepMind, ATB Financial, Director of Artificial Intelligence at ATB Financial, and various other places. So master students, just find someone to work with. you could work with me, for example. I'll write down my email address again, nikkei@hpqc.org. And that's one way you could start working on a quantum computer. We have access to them. You might not have access at your university. Can you further explain the use, application of quantum computing in finance? I could give an entire lecture on that. I told you if you took my entire quantum computing course, you would see that I have a lecture just on quantum finance. But to explain this in simple terms, if you understand financial calculations, for example, solving partial differential equations, one of the most famous ones being the Black-Scholes equation. This is a matter of solving partial differential equations fast, and on a quantum computer, there's algorithms to make use of the fact that qubits can be in 0 and 1 at the same time. There's ways to actually make use of that fact that a qubit can be in 0 and 1 at the same time in order to speed up the calculations of solving partial differential equations. So I don't have enough time to give a whole course on the most interesting quantum algorithms. I gave you the simplest ones because they're easy to teach. To teach quantum finance, you'd probably need to you first need to know what a quantum Fourier transform is. You need to know what a controlled NOT gate is. I didn't talk about that yet. You need to know what a Pauli Z gate is. I don't think I talked about that yet. Although I mentioned it, I gave you the matrix for it, but basically there are a lot of prerequisites you would need to get to that stage. But if you wanted to learn about quantum finance, you can talk to me. I can organize a course just for you. You mentioned that there is an unlimited number of quantum gates. Can you please elaborate on that? That's a very good question. So in quantum computing, this is just some stuff about quantum hardware. In 2016, where we were, now we are, we had a 17 qubit machine just a little bit later in 2017. And then we had a 50 qubit machine later in 2017. So they're getting bigger. If you want to see what they look like, this is what the quantum computers look like. Now to answer your question, how can you have an unlimited number of quantum gates? So in quantum computing, we have qubits, which are given by wave functions. This qubit can take the form of A0 plus B1, such that the probabilities just have to make mathematical sense. So the modulus of A squared, sorry, the modulus of A squared plus the modulus of B squared has to equal 1, because the probability of finding the state in 0 versus the probability of finding the state in 1, the sum of those probabilities has to be 1. So we can, what is a way we can parameterize A and B such that the sum of the squares equals 1? We can say sine of theta 0 plus cos of theta 1. Okay? Square of sine theta plus the square of cos theta, it equals 1. So for any value of theta, theta can be 0, it can be pi, it can be 0.21345, it can be, theta can be anything you want, 0.9321. And if you want another value of theta, just add some more digits here. You can make it as precise as you want. You can have as many digits as you want. So any value of theta works. You don't just have zeros and ones. You have an infinite number of possible qubits, qubit states. Now, if we can have an infinite number of possible qubit states, you can transform your qubit states. Let's just say we have a matrix like this for our gate. So remember, we had the NOT gate was just 0, 1, 1, 0. Imagine if we now have this quantum gate. It turns the qubit into cos theta 0 and sine theta 1, or whatever it is. We can make theta whatever we want. So we can have an infinite number of quantum gates available. In a classical computer, we don't have an infinite number of gates available. We can turn 0 to 1. We can turn 1 into 0. There's not much more you can do. In a quantum computer, you can turn 0 into any linear combination of 0 and 1, as long as you have the square of the coefficients, the sum of the squares of the coefficients equals 1. So we can have any value of theta. That seems to be the last question that I see in the chat. I hope that I answered all your questions. I didn't have time to read them thoroughly, but based on what I see in my just glancing at the questions, it looks like I have answered all of the questions. And if I have not, then please let me know. I see one new message. What is the main hurdle to low-cost quantum computing? Well, you can imagine it. I can speak here forever, but you can imagine that I told you at the beginning that we have, let me go back to the first slide here. We have quantum mechanical states, like photons can be put into these superpositions of zeros and ones. But in order to do that, we have some device that turns the qubit into some state that is in a superposition of 1 and 0 at the same time. Making those quantum mechanical gates is not as easy right now as it was for making classical gates. Classical gates are simpler, quantum mechanical gates are more complicated. And then the main hurdle now is we have something like 1 over root 2, 0 plus I over root 2, 1. So we're a little bit in this path and a little bit in this path. These states are delicate. So you can imagine if I measure which path is the photon in, is it in this path or is it in this path? That measurement collapses this wave function into either 0 or 1 with 50% probability in both cases. Now, what if a particle of dust were to land on the quantum computer, were to land on the qubit? That dust now knows if the qubit was in this path or in that path. That particle of dust has measured the qubit. It has collapsed the wave function. It has opened the box, and it has detected whether the cat was alive or dead. And you can imagine it's not easy to make a quantum computer if, you know, my laptop has dust going in it all the time. There's a fan that's spinning around, and that fan is full of dust. And that doesn't affect the classical computations going on my laptop. On a quantum computer, this particle, this dust or whatever it is, whether it's a vibration, whatever it is, if it collapses this wave function, then I'm back to having a classical computer. This is no longer 1 over root 2, 0 plus 1 over root 2, 1. I now just have 0 if that quantum mechanical state is collapsed. If it is measured by anything, by a piece of dust, by a frog that is looking at it, basically, if you open the box and you look at it, then the wave function is collapsed and you're back to a classical computer. You can also imagine that these calculations probably have to be done at very low temperatures. And the reason for that is that these quantum mechanical states, the higher the temperature, the more vibrations going on in your hardware, the materials that are this quantum computer is comprised of some materials. Those materials are vibrating. Those vibrations are going to be causing damage to these very delicate components. So that is the main hurdle. It's the fact that you need to sustain these states for a long time, and you actually have to manipulate these states. I'm telling you about qubits being spin up or spin down of an electron. How hard do you think it is to take an electron that is spin down and turn it into a spin up electron? It's spinning this way, and you want to take that electron and make it spin that way. That is not easy to do. With a classical computer, I can change the voltage. I can take a magnet that's north polarized and make it a south polarized magnet. I can make a disk. I showed you there's a disk, a CD, with pits. When there's a pit, then it's a 1. If it's no pit, then it's a 0. These CDs, they have lots of 1s and 0s, and I can make those 1s and 0s just by creating dents or small pits in the CD. How do I create a system with 100 electrons that are spinning up or down at my own desire? That's something I don't even know how to do it. but there are some experimentalists that are working on it. And there are quantum computers right now, and they work. They work, but they're just not yet big enough to do large-scale quantum computation. But that is the idea. The idea, their hope, the people working in quantum computing, their hope is that maybe sometime in the future we will have more powerful computers and we have more sustainable computers. Instead of that big picture I showed you at Oak Ridge National Lab where they have so many computers working on the same problem, so many computers, a computer with 20 million CPUs being used to calculate something. It's using the amount of power that a small city would use. These quantum computers are only using 12 kilowatts of power. They might be more sustainable if we can find a way to make them and scale them up to the size required to solve real-world problems.
Thank you, sir, for the valuable talk. Let's conclude the session. I invite Mr. Anu Thomas, Assistant Professor, Department of Physics, St. Stephen's College, Uravur, for vote of thanks.
Good evening to all. As a person pursuing physics, I am grateful for attending this session on the fundamentals of quantum computing, which promises to revolutionize future computing. I hope everyone else in the audience also feel the same way. I would like to take this opportunity to express my gratitude to Dr. Dattani on behalf of Quaesitio 2024 and St. Stephen's College, Uravur. Thanking you very much, sir, for shedding a very large amount of light into a revolutionary idea, which is quantum mechanics. Thank you very much, sir.
You are welcome.
Thank you, sir. The next session, that is session 6 of will be started tomorrow at 9:15 a.m. Thank you.
Tomorrow we will have a different Zoom link. It will be shared to you and you use that particular link to log in.